in section 12.3, we do the calculus in polar coordinates. So we're going to find slopes and of tangents in a very similar way that we did for parametric equations as well. And we're going to find points of intersections and areas of polars, under these petals of flowers inside cardioid, stuff like that. And then we will finish the chapter with arc length on polar curves. Alright, so and last time for tangents we found the derivative of a function in the polar system. Of course, even though when we want to find the derivative of a function, it's not just r prime equals taking the derivative of the function in terms of theta. No, that's not the way we do it, because these functions, these polar forms, these polar functions are described in terms of parametric functions. So we have, and that's because, and it all stems from the fact that x is related to r cos theta and y represents r sine theta, where r in this case is the function for which we do the operations for. And well, we did the derivation here, which ultimately led to very simple derivation here, so nothing really crazy. We did an example how to find the derivatives in the same way as we did the differentiations for parametric form. We differentiate the x equation, we differentiate the y equation separately, and then we put it together into a single expression. Then we found the equation of a tangent line. But of course, the equation of the tangent line that we found happened to be in rectangular form. So in order for us to see the whole picture, the graph of the function in polar and the graph of the line, we converted the given line into its polar version, so we can see the whole thing together. And I believe, let me just briefly. Hopefully it's still here. No, it's not here anymore. For whatever reason, it's not here anymore. I don't know what happened here, but well, anyway. So now we're going to find any points of vertical tangencies. And for points of vertical tangencies, well, you might remember this from Calculus 1, that when you want to know where does a function has a vertical tangent line, what we need to do in this case, set the denominator equals to 0. Alright, let me write down the derivative again. So for the derivative, dy dx, I know dy dx, but in this case we have a function of theta. But ultimately that's because the derivative in parametric form for these functions rely on an x equation, which is a function of theta, and a y equation, which is also a function of theta. Alright? So we got cosine theta minus 2 sine cosine, or 2 sine cosine, whole thing over sine squared theta minus cosine squared theta minus sine theta. Alright? Well, in this case, it's important to highlight this. The fact that points of vertical tangency are obtained by setting the denominator equal to 0. Alright? And let's highlight what we are going to set, right? So this is the quantity that we set equal to 0. Okay, so, and yes, in this case, this one is going to take a couple minutes, because we will have to use trigonometric identities, do a few algebraic arrangements here and there. So sine squared theta minus cosine squared theta minus sine theta equals to 0. Well, in this case, back from trigonometry, when you solve these trigonometric equations, you'd rather have an equation. Well, when it comes to an equation like this in particular that is in quadratic form, you might want to have everything in terms of the same trigonometric function. Notice the majority of the functions that we have is the sine function. So you might want to convert, in this case, the cosine squared into terms of sine. So this will be sine squared theta minus cosine squared, which is 1 minus sine squared. Alright. So I'm changing this cosine squared into 1 minus sine squared. And minus sine squared. I mean just sine, not sine squared. And well, let's distribute the negative here. So that's going to be sine squared theta minus 1 plus sine squared minus sine. And combining like terms, notice the sine squared, we have two of them, and we can also write this in terms of a quadratic equation. That'll be 2 times sine squared theta minus sine theta equal and minus 1 equals to 0. Notice this is a quadratic equation, and well, we can solve this equation by factoring. There's many ways to factor trinomials, right? So I will just give you the result of factoring this. So in this case, sine theta minus 1 times 2 sine theta plus 1. You can do this by guess and check, or remember the diamond method I showed you, and there's other methods to factor trinomials whose leading coefficients are different than 1, right? So there's different ways. So using the zero product property, sine theta minus 1 equals to 0, which means sine theta equals 1, and on the other hand, 2 sine theta plus 1 equals to 0, which means sine theta equals to negative 1/2. So now we would be looking for the angles for which, well, number 1, sine equals to 1 and sine theta equals to negative 1/2. And well, for negative 1/2, we have two potential solutions. Number 1, that's 7 pi over 6 and 11 pi over 6. Alright? Keep in mind that in this case we want sine to be a negative value. Recall that all students take calculus. That's to determine which functions have positive signs in the corresponding quadrant. So in this case we want, okay, sine is positive in the second and the first, so the only two possibilities is the third and the fourth quadrant. And in this case, well, that's a negative 1/2, negative 1/2, and that's pretty much 7 pi over 6 and 11 pi over 6 respectively. Alright? And for sine theta equals to 1, the only possibility here is, what angle has a sine equal to 1, by the way? Pi over 2. Alright, but we need to be careful. What about this? Alright, so I think we got the graph of a cardioid for this, remember, from last time? Well, this one looks more like an apple. And then in this case, here is where we have our vertical tangencies, the 7 pi over 6. And notice in this case pi over 2, that pi over 2 right here, which is this point right there, it's really not a vertical tangency. Do you see instead this is a cusp or a sharp corner? Alright, so you need to be careful when looking at the graphs. Where are those or rather, what do some of the solutions to the equations that we do here really represent? So, and that's another issue that will come into play well later in the next type of exercises. So this is a cusp, and this is the vertical tangencies. All right. Okay, for the next topic, points of intersection. So points of intersection for polar curves, well, I mean, you know how to find points of intersection when we have algebraic functions. All we do is we're given two functions or three functions, well, depending on what we're doing, set them equal to each other pairwise if you have more than two, and solve the equation for the variable x, y, whatever variable you're dealing with, right? Yes, we're going to do exactly the same with trigonometric functions. However, it might be a little tricky to do when it comes to that. So, and also, well, notice that we are working in the polar system first. We will get those points of intersection in polar form, and then we will have to convert those into Cartesian form. Well, you know those formulas to convert those kinds of points, but of course we're going to review those here. We did that last week, I think. And the reason why we're going to do the whole thing is because it depends on the questions. It depends on whether we will, on my MATLAB, you will be just asked to submit the results in polar form or in Cartesian. You will have to go all the way to the Cartesian form. So let's go ahead and find the points of intersection in Cartesian form. And well, there's some important point right here before getting to the exercise. We will use, and it is very, very important, not just algebraic techniques, but also graphic techniques, as you will see some of the issues here. And we highlight this because sometimes when we are working on some of these exercises, it's a little bit frustrating submitting answers that are not really the answer they're asking for, and that's because those answers do not represent a point of intersection, or some information is missing, some information that otherwise we cannot get algebraically. Okay, so let's have a look. Let's set these two equal to each other. That's -6 cosine theta equals 2 minus 2 cosine theta. So, well, let's solve the equation. Let's have all the trigonometric functions on the left hand side, everything else on the right hand side. Let's add 2 cosine on both sides to get -4 cosine theta equals 2. And cosine theta equals -2/4, which reduces to -1/2. All right. Well, so in this case, we're looking for angles whose cosine is -1/2. Number one, if you want to recall, all students take calculus, mnemonic. Well, we want cosine to be negative, so cosine is positive in the first and the fourth quadrant. That means we will have the two angles in the third and the second and the third quadrant, right? So, and by definition, this is adjacent over hypotenuse and adjacent over hypotenuse. Which angles are these? I believe these are 2 pi over 3. And 4 pi over 3. All right. Those are the two angles for which cosine is -1/2. Okay, so now this is what we need to do. We need to compute those points of intersection in both polar form and Cartesian form for each of the two angles. You know, it's like going back to plugging in the original equation and all that. All right, so let's see. What are we going to have? So for theta equals to 2 pi over 3. So we have the angle 2 pi over 3. We need to find out what the radius is. Well, recall that when you solve a system of equations and you get, well, typically you're given a system of equations with two unknowns, with variables x and y, right? And typically we go in alphabetic order. We get the value for x first, and then we go back to any of the equations to find the value of y. But in this case, we're not dealing with x and y, but we're dealing with r and theta. So we can go back and plug in this value of theta up to pi over 3 to your favorite equation in this case, and in this case, well, by favorite, I mean the simplest possible, and I think it's the first one, isn't it? So r equals -6 cosine of 2 pi over 3, and well, cosine of 2 pi over 3 is, well, we already got that. It's -1/2, isn't it? We got that from solving the equation. So that's a -6 times a -1/2, which is +3. So that means that we have another pair of the form. So I know what I'm going to do here is a lot of symbols. So that's just so you can see what are we representing here. So r theta is a radius of 3 and an angle of 2 pi over 3. So that's what we have. Now we need to convert this point into Cartesian form. And well, there's two equations that we need to use in order to get that. Number one, to get x, r cosine theta, and y equals r sine theta. All right, so this is 3 cosine 2 pi over 3, 3 sine 2 pi over 3. Well, so 3 cosine pi over 3, so cosine 2 pi, well, we already did that. Wait, no. So cosine 2 pi over 3, which is 3 times -1/2, and that's a -3/2. All right? And sine, which is 3 root of 3 over 2. So that's simply 3 root of 3 over 2. So now we have the corresponding x, y of -3/2, 3 root of 3 over 2. All right? I'm using different colors to show the different representations in polar and in Cartesian. And we just did it only for the angle 2 pi over 3. Let's repeat the process for for 4 pi over 3. Okay, so for theta equals 4 pi over 3. So we're going to we need to find the radius, so we only know the angle. We need to go back to any of the equations. R equals to -6 cosine 4 pi over 3. And cosine of 4 pi over 3 again is -1/2, so that's -6 times -1/2, which is 3 again. Okay, so now that means that we have a point of the form r theta of 3 4 pi over 3. Okay, and we need to convert this point into its corresponding rectangular coordinates. So, and again, we are going to use the same relations that we did before. X equals r cosine theta, and y equals r sine theta. So 3 cosine 4 pi over 3, and 3 sine 4 pi over 3. And on the one hand, well, cosine pi over 3, that's 3 times -1/2, and that's a -3/2 also. And well, sine 4 pi over 3, that's -√3 over 2. All right. Do I have the correct signs? Yes. All right. So these are the points. Oh, let's express in a different color the point in Cartesians. X, Y to represent, to denote that what I'm going to repair that I'm going to write is a representation in Cartesian. So that's a -3 halves, comma, -3 over 2. Okay, so we have 2 points of intersection right here, right? And well, so let's say this is a question from my MATLAB, and you submit, well, either, well, depending on what you're being asked to submit, whether this is the polar representation or the Cartesian representation. But I will assure you that you're gonna get this wrong. Why? Okay, let's go to the graphing calculator to show you why. So, oh, okay, I see. Hold on. Mode, polar. Oh, yes, I was in parametric form, so that's why we didn't. Well, never mind. Oh, there's nothing. Okay, so let's type the equations. R equals -6 cosine theta, close parentheses, and 2 minus 2 cosine theta. All right, and graph. Let me zoom fit. Okay, how many intersection points did you see? How many did we find algebraically? We found 2, right? Well, technically we got 4, but in this case 2 are the same because one of them is representation in polar, the other one is representation in Cartesian. All right, so the ones that we got algebraically are this one and that one that represent the 2 pi. So from the origin, or rather from the pole, more properly, this is the 2 pi, the angle of 2 pi over 3, and this is the angle of 4 pi over 3 that we got algebraically. But what about this one? I mean, clearly, what's that order pair? 0, 0, and 0, 0. It's the same whether in Cartesian or in polar. All right. So let me do a mini graph real quick, or maybe not, because we already saw that in the graphing calculator here. So 3 points of intersection. And I'm going to list only the rectangular ones. So one is going to be -3/2, -3√3 over 2, and -3 over 2, comma 3√3 over 2, 0, 0. And well, let's highlight something here. Let's highlight the fact that we got this algebraically. And the fact that we got this graphically. All right. So this is very common in the polar world. All right. All right. So let's do another example. Same. Let's find in Cartesian form, and well, of course, first we find them in polar form, then we have to do the calculation for Cartesian form for this pair of functions. So let's see. We're going to set 1 plus sine equals 1 minus sine. Let's have all the signs on the right hand side. That's going to give us 2 sine plus 1 equals 1, and then this will be subtract 1 from both sides to get to sine theta equals to 0, which is the same as sine theta equals to 0. Alright? So when we solve this mini equation right here, we're looking for the values of theta that typically we do this in one term within the interval 0 to pi, for which sine equals to 0. What are those values? 0 and pi, right? Well, technically to pi as well, but to pi is a repetition of 0 because of the periodic properties of these trigonometric equations, or rather functions. So that means theta equals to 0 and pi. Okay. Well, so let's repeat the calculations to get the value of r, to get another pair in polar form, and we can go back to our favorite equation. And well, I mean, in this case, either equation is fine. I'm just going to use the first equation to get the values of r. So for r equals to 0, we should get r equals to 1 plus sine 0, which is sine of 0 is 0 plus 1, that's 1. That means we are going to have another pair that looks like r theta equals 1 comma 0. That is, it's 1 unit away from the pole with an angle of 0 degrees or 0 radians with respect to the polar axis, or the analogous x-axis in the Cartesian coordinate system. All right, so let's do the second one for r equals to pi. R equals 1 plus sine pi. Sine pi again is 0 plus 1. That's also, oh, wait a minute. Yes. No, that's fine. 0. No, not 0. That's 1. And well, we're going to have a polar representation r comma theta equals 1 comma pi. All right? Okay, so we have the points in the polar system. We need to find those in the corresponding Cartesian system. And to do that, we use, again, our relations, r cosine theta for x, which is r equals 1 times cosine theta. Well, that's going to be 1. And y equals r sine theta, which is 1 times sine 0, and that's 0. Sounds good? And for the other point, x equals r cos theta, that's r, or rather 1 times cosine pi, and y equals r sine theta, which is 1 times sine pi. And well, cosine of pi, be careful, I believe that's a -1 times 1, that's going to be -1, and sine pi, that's 0. So what do we have? We have the Cartesian representation of each point. So this r theta becomes xy, and that's 1 comma 0. xy -1 comma 0, and we are essentially done finding the points of intersection. How about we go to our graphing calculator to find out if this is true or if we're missing any information. All right, so clear every other equation that you had there and type the new one. So that's 1 plus sine and 1 minus sine. And let's graph. And zoom. Let me do zoom fit. How many points of intersection do you have there? How many did we find algebraically? 2. So which ones? Well, this is most likely the 1, 0, and then the 1, or yes, 1, 0, or 1, yes, it's also 1, 0 and 1, 0 on both versions. And this is the negative 1, 0 or 1, pi, depending on the system. And well, which point is this? Whether in polar or Cartesian? 0, 0, same, right? So I'm going to algebraically and also 0, 0 graphically.